Select the automated indentation and thickness batch analysis tool. This tool is adapted for the analysis of raw data from a 3D normal indentation mapping and/or 3D thickness mapping of a sample. The sample must be composed of an elastic layer bonded to a rigid layer at least 10 times stiffer than the elastic layer, for example, articular cartilage over subchondral bone. This tool has been designed to allow a simultaneous and more convenient analysis of large sets of data resulting from 3D normal indentation and thickness mapping tests. It reads any map file containing the pixel X, pixel Y, position ID, subsurface ID, scan X, and scan Y columns of a sample. It also reads the associated Mach-1 text file containing the raw data of a 3D normal indentation mapping and thickness mapping saved from normal indentation functions and find contact functions respectively. It is a semi-automatic software as user interventions are required when manually adjusting the position of the cursors to locate the correct point of contact of the articular cartilage and/or subchondral bone. For each new sample or dataset to be analyzed, click the button New Sample on the top left corner of the software. Files must then be imported in the tool to associate each normal indentation and find contact curves to their corresponding mapping positions. To achieve this, click File in the menu bar and select Import.map to import the map file containing information on the pixel X, pixel Y, position ID, subsurface ID, scan X, and scan Y of the sample. Once imported, the information stored will appear in the Results Table field at the bottom of the tool. Note that if a thickness analysis has been previously performed and saved in a map file, when imported, the tool will automatically recognize the thickness analysis values and consider them in the current analysis. The second step is to import the raw data collected from Mach-1 motion. Click File in the menu bar and select Import.txt to import the raw data text files that contain the normal indentation and find contact functions. As you can see, the curves will now be available in both graphical displays. The current point ID field will be filled with the positions defined in the imported.map file, and the user can select a position to display its corresponding find contact curve shown in the left graphical display and the normal indentation curve shown in the right graphical display. Note that if the Mach-1 motion thickness or text file is not selected, it will display the following message shown in the left graphical display. Also, the position IDs without thickness field will show the names of the subsurface IDs and the position IDs of missing thicknesses. In this case, since we have not chosen the entire file, all position IDs on each subsurface are unavailable or missing. From the Edit option, the user can specify a maximum % error. This is the difference between the scan X and scan Y coordinates in the map file and between the X and Y positions in the data file. Those coordinates are compared to determine which position ID corresponds to which curve in the data file. Also, from the Edit drop-down list, the user can toggle on and off the cursor name and coordinates. Once the raw data and list of positions have been imported, the next step is to select which characterization is desired to be extracted from those curves. To select these options, click on Analysis in the menu bar and check all the characterizations that are desired to be extracted. The checked characterizations will light up in green under Mechanical Parameters. An extra column with the appropriate headers is automatically created in the Results Table field for each selection. The analysis columns can be deselected or removed by unchecking it from the Analysis drop-down menu. These are the following characterizations that can be extracted from the raw data obtained from the 3D normal indentation mapping and 3D thickness mapping. The maximum load corresponds to the peak load in newtons of the data curve. Load at displacement corresponds to the load in newtons at a desired displacement in millimeters. Load at time corresponds to the load in newtons at a desired time in seconds. Relaxation time corresponds to the time necessary for the load to fall from its peak value using the following equation. Structural stiffness at displacement is the stiffness at a specified displacement and is given by the following equation. The instantaneous modulus at displacement in units of megapascals corresponds to the instantaneous modulus when the Hayes model is fit up to the desired displacement in millimeters. The instantaneous modulus at strain in units of megapascals is the instantaneous modulus when the Hayes model is fit up to the specified strain. For example, if 20% strain is desired, the software will compute 20% of the thickness and fit the model up to that value. It should be noted that the instantaneous modulus characterizations could only be computed when a thickness dataset has been imported. The algorithm to obtain these characterizations are from the 3D normal indentation mapping and 3D thickness mapping tests. They consist of extracting the vertical thickness from the fine contact curve and extracting the surface angle from the normal indentation curves. Then the vertical thickness is multiplied by the cosine of the surface angle to obtain the thickness of the elastic layer. Once the thickness is known, it can be input into the Hayes elastic model in spherical indentation and fit onto the experimental normal indentation curve. This algorithm is repeated for every position ID to complete the mapping of the entire surface of the sample. In this example, I will analyze the 6th position ID on the lateral condyle of rat cartilage. I will select all the analysis options for the purpose of this demonstration, however your choice will vary based on the objectives of your study. I will choose the maximum load at displacement of 0.04 millimeters or 40 microns, load at time of 2 seconds. As you can see, you have access to a miniature version of the normal force versus time graph on the top left of the right graphical display. I will then choose relaxation time, the structural stiffness at 0.03 millimeters or 30 microns, instantaneous modulus at a displacement of 0.02 millimeters or 20 microns, and an instantaneous modulus at 20% strain. Once the desired characterizations have been selected, the user can proceed with the analysis. For each position, if the fine contact curve recorded has a typical load displacement behavior and the surface angle is less than 60 degrees, the curve can be analyzed to extract the thickness. The automatic mode will attempt to find the surface, shown by the red cursor, and the interface, shown by the blue cursor, from the fine contact curve shown in the left graphical display. The user should always verify that the automatic mode has successfully positioned both cursors. If this is not the case, the user should drag the cursors at the correct position of the surface, that is, the position where the load starts to increase, and the interface where there's a sharp increase in the load. Once verified, click Save Thickness, and the thickness will be computed and reported in the result table field in the corresponding position row. Otherwise, if the thickness could not be extracted from the fine contact curve, click Bad Recording Thickness, and the software will automatically advance to the next available position ID. As mentioned earlier, if a thickness analysis had been previously performed and saved as a map file and imported, the cursors will automatically be positioned at the saved location of the surface and interface. Once the thickness has been analyzed, define the correct input parameters for the elastic model, such as the indenter shape, indenter radius, and Poisson's ratio. The thickness is automatically input into the sample thickness field once the user clicks on Save Thickness. After verifying that the corresponding normal indentation curve has been collected and has a typical load displacement behavior with the blue curve predicted from the Hayes model superimposed on the normal indentation curve, click Save Indentation. All mechanical parameters that have been checked will be computed and reported in the result table next to the corresponding position row located at the bottom of the tool. Otherwise, if the indentation curve cannot be analyzed, click Bad Recording Indentation and the software will advance to the next available position ID. Finally, when all the characterizations are acquired for all the position IDs, click File in the menu bar and select Save.map file. Select an appropriate name and location for the file. The results are now ready to be mapped onto a top view image of the sample. A user license is required in order to access the semi-automated indentation and thickness batch analysis interface.